Hi, I'm Ray, G4NSJ. Now I want to talk to you about, I've got an article here, high performance common mode chokes. Right, and there's a couple of, mine are not high performance, I don't think. That toroid, that core, I don't know what it is, I just found it. And we'll go into that later. Same with that one, I've got a box of these, and these were just experimental things. Now, before we go into this article, thanks Roy for sending me this, the link to this. A friend of mine, Roy, sent it to me, and it explains things so well. Before we go on to the choke, I can't unfortunately stick the pictures up on the screen. There are all sorts of things here because of copyright. I'm not sure, I don't want to get done for it. But this article is by Steve Hunt. There we are, G3TXQ says at the top here, so presumably it's by him. Before we start looking at this, let's look at Coax. Now he says here, you think of Coax as a two-core line, don't you? You've got the inner and the outer, all right? So it's two conductors, isn't it? He says here, Coax cable is in fact a three-conductor line. The third and independent conductor is the outside surface of the braid. Now you're thinking, how can it be a three-conductor line? There's inner and outer, there's only two. As he explains in his article, and I do urge you to have a look, I'll put a link at the bottom of the video, down there, look, I'll put a link. Have a look at it and read it. Some time ago, I decided to build a Flowerpot antenna, a so-called half-wave coaxial dipole. And people said to me, oh, it's not a dipole, it's a badly designed quarter wave ground plane aerial. Other people said, no, it's an end-fed half-wave dipole. It's not, it's a centre-fed half-wave dipole. Now already you're thinking, some people are thinking, no, it's not, no, you're talking rubbish. Read this article. Let me just explain what this chap says. When you pump RF up that, there's what you call the skin effect. So the RF travels on the outside. There's the inner conductor, right? The center core travels on the outside of that. All right. The braid, there's the inner core in the middle. There's the braid. It travels on the inner surface of that braid in there. Okay, that's the two conductors that we know about. Right. It doesn't go through the braid to the outside. This is what he says, and he explains it very well. The third conductor is the outer surface of the braid. This is hard to grasp for anyone who is new to RF engineering. But the skin effect is a dependable fact, and so are all its consequences. So it's a fact. So don't shoot me, I'm the messenger. Understanding that, all right, as he says also, you can put this through water, you can put it through metal, you can coil it up. You can do what you like with coax. Put it through a metal bulkhead or whatever. It doesn't have any effect on what's going on inside. Okay, that inside, as he's put somewhere, is like a private world, right? The inner of the braid and the inner surface of the braid and the surface of the inner conductor. That's where all the RF is. That's where you're sending your signal. What happens on the surface of the braid outside is totally different. Right, we're going to have a quick look at the blackboard now. This video isn't about Flowerpot antennas, but I just wanted to show you this. The article says that the RF comes up here. Right? This is a quarter wave. So if we cut the coax there, we're putting RF up here, say from our 2-meter radio. That's a quarter wave, so that will radiate, won't it? It's a quarter wave radiator. This is the braid here. Okay, so that's sticking out of the center there. The RF is on the outside of that one, and the inside here. Okay, not the outside. When you cut it off here, this comes out, it spills out onto the outside. Okay, so you've got RF on the outside of that, and now on the outside of the braid here. Doesn't affect what's going on the inside. Do you see that? When I read this it all started to make sense. I always thought this was the case anyway, and other people just poo-pooed it. No, that's rubbish. They came up with various ideas about this aerial, but this makes sense. That's a quarter wave. The outer surface of the braid is a quarter wave. This is the sort of choke thing, okay? So it all stops there, all right? That's the idea of that. So there is the lower quarter wave of your dipole, there is the top quarter wave of your dipole, and it is fed in the middle. It's a centre fed half wave dipole. Now, if you want to argue with that, don't argue with me, because I'm not an RF engineer, never have been and never will be, because I'm not clever enough. But this, to me, makes all the sense in the world. I can now get to grips with exactly what a Flowerpot or coaxial dipole is. Right, let's take an HF dipole, all right? There it is, HF dipole for whatever, let's say 40 metres. There's your coax. I mean, you don't normally have plugs on it. There's your coax going up to the centre of it. So it's a 40 metre dipole. It'll only work on 40 metres because you fed it with coax. If you want to feed it with open line feeder, it'll work on other frequencies and things. Right, that goes up. No choke, no balun, no stuff, no gubbins, right? Inner to one bit of the dipole, outer to the other bit of the dipole. What's going to happen? You're going to get these two elements of the dipole are radiating, aren't they? They're putting your signal out and you're working DX. Excellent. But what else is going to happen? RF will go up the inner surface of the braid and spill out over here. It'll spill out and come down here, down the outer surface of the braid. So you've got a leg there of the dipole and a leg there of the dipole, and now a leg here of the dipole. You know, with a dipole, there's a centre dipole. What you want is the current peaking in the middle, isn't it? Like that. That's the current. Voltage that end, voltage that end. High current in the middle, because that's just the bit that radiates. Okay. If you've got this radiating, it can totally mess up that pattern. So you've got to somehow stop the outer here becoming part of the aerial. It ends up, as Steve says in his article, you end up, it's not a dipole, it's a tripole, as he's put it, which is very good, I like that. You end up with a weird sort of tripole effort that is not efficient at all. So that's where this comes in. Now, coiling this all round a toroid, right, doesn't affect what's going on inside, because someone recently said to me, if you do that and this greatly attenuates, say 2 to 30 megs, really attenuates everything, you know, like 30, 40 dB or more, well, you've lost your signal, surely. You know, the station you're trying to listen to, you've attenuated his signal by kind of 40 dB. No, because inside is like the private world. What's happening outside here doesn't affect that at all. So that whizzes round as it would do, unaffected by the outside. What this does, it affects the outer surface of the braid. So that presents a very high impedance, perhaps a couple of thousand ohms or more, to any RF that's on the outside here. So it can't, there's your aerial, there's your dipole, right? That is a really high impedance to any RF on the outside. So that is stopped there, and then down here, what's that? We're getting noises. Okay, do you see what I mean by that? I'm not very good at explaining this because, as I said earlier, I'm not an RF engineer. And also, even if I did understand the real in-depth mathematics and technicalities of all this, I don't think you'd want to hear that, because I know a lot of you are newcomers. You're starting out, you know, you don't want me to go on about square roots of that, whatever they are, I don't know, square roots of something or other, flowers. Flowerpot, yeah, Flowerpot antennas probably have square roots, don't they? Anyway, moving on. So that's what that does. It basically takes RF off the outside of the coax, because you're going to have it where this is cut. The coax is cut to feed each leg of the dipole. It's going to, as I said on the Flowerpot antenna, it's going to spill over there and come back down the outside to make a tripole. I had a comment a little while ago from someone said, I wish this bloke would get on with it instead of rambling for. The video's only been going about 6 or 7 minutes. I've hardly rambled. I'm now going to get the NanoVNA, okay, and we're going to have a look at this to see what it does. It's all very well fitting things like this, okay. You know how people say, "Oh, coil up coax," where your dipole is fed. Coil up your coax like that to make a sort of choke thing, a balun thing, an RF thing. Apparently that doesn't work too well, according to this and according to a load of other stuff I've read. So it's got to be true. It doesn't work too well. You know these clip-on RF. Well, I've got a bag full. You know, they clip on. They work apparently. I've never tried it, but you'd have to have a whole row of them. You know, like there's your dipole. You'd have to have a whole row of them down here for them to begin to do any good at all. You want something like this where it's coiled round and round and round. And as I say, I'll put this on the NanoVNA in a minute. Now these toroids here, these rings, I don't know where, I think they came from computer power supplies. I've no idea. I've got a box full, I don't know what they are. So it'd be interesting to see exactly what these do. I have ordered, and I'm hoping it will turn up today, I've ordered an FT240-31. And from what I understand, the -31 is the mix. Okay, it's the mix in here, what it's made of. You know, the amount of iron and stuff and gubbins they put in these to make. That is the mix. 31 and 43, I think, are the good ones. I've ordered 31. The 240, apparently, I didn't know this, 240 is the first 2.4 centimetres, and that's the inner diameter. So 240-31 is 2.4 centimetres inside, 31 mix. There you are, live and learn. So that's good, isn't it? I'm just going to butt in here. I lied, it's not 2.4 centimetres at all. It's 2.4 inches, and I think that's the outside diameter. The 31 and 43 mix, they're good for HF, okay? Just bear that in mind. I'm not talking about VHF at all in any of this, because I'm an HF man, you know, I like the old shortwave bands. So, yeah, ignore what I just said. I lied to you. When I get the toroid, when it turns up, I shall measure it with a ruler. Then we'll know exactly where we are. Right, let's get this NanoVNA out and start looking at stuff. Right, this is my dark box, okay? I have to put the NanoVNA in there because all these lights reflect on the screen. Now, these are the clamp-ons, right, or clip-ons or whatever. And what I'm doing, I'm poking the wire through once like that, then twice, okay, and then 3 times. You see that? To see what happens. Also, I think I start off by having 2 like that, just the wire straight through 2. First of all through 1, then through 2, then start the coiling. So let's have a look at that. At 13 megs, there's 3 dB attenuation. That's the wire just going straight through the clip-on. So that's 13 megs, 3 dB. If I put a second clip-on, clamp on, we've now got 2 in a row, and at 13 megs, 4.8 dB. So it hasn't doubled. You'd think it would double, wouldn't you, or whatever. It hasn't at all. This is why you would need a whole row of them. Now, instead of having 2, let's go back to the 1, and the wire goes through it once. I'm going to poke the wire through it for a second time. So we've now got a turn on there instead of straight through. 7 dB at 13 megs. So that shows that you are better off coiling it round and round a ferrite ring than having lots of them, lots of clamp-ons. You know, you're better to coil it round. Let me see if I can get it through a third time. Minus 12. There we are, 12 dB attenuation at 13 megs. I think I got muddled up with my turns there. So it was straight through, all at 13 megs, 3 dB. 2 of them in a row, 4.8. So it hasn't doubled, it's just gone to 4.8. Do a turn on that, you've got 7. So from straight through 3 dB, one turn you've gone to 7, so that's good. I think it was 3 turns, 12 dB. So that's what I'm saying, you're better off coiling it round. We're now going to look at this. I'm going to stick this on the NanoVNA and see what we've got here. Going to stick to 13 meg still, and let's have a look at that. Now this is the green toroid with the plugs on each end. Again, 13 megs, 17 dB attenuation. Now that isn't a lot. You might think, well, that's not very good, is it at all? No, it's not. It's because this toroid, I believe, is out of a computer power supply. It's not meant for HF at all. If I find where it is best down, let's have a look. Let's just go to minimum. At 2 megs, it's 22 dB. That's its best spot. Okay, it's turned up and I've wound that. What was I saying about the measurement? Yeah, the 2.4 is the outside. So when it says it's an FT240-31, the 240 is 2.4 inches outside, okay? I've wound that. There's a close photo of it. And what I've done, as you can see by the photo, I've wound half of it one way, then half the other way. Can you see that? Goes that way and then the other way. So the two cancel out. If you get RF voltages built up on here, that will cancel out. So it did say in the article somewhere that he didn't really think it was necessary to do that, but there we are. It doesn't make any difference, does it? I've ordered a box to put this in. Use a plastic box, not metal, because metal will muck it all up. Use a plastic box. That hasn't turned up yet, but let's do some tests on this now. A proper ferrite ring made for the job, made for HF, rather than some old computer power supply thing I found. Okay, look at the video clip. Okay, on 2 megs, 24 dB of attenuation, that's 2 megs. 4 megs, 27 dB. 7 megs, 28 dB. Just going roughly through the amateur bands. 10 megs, 29 dB. 14 megs minus 30 dB. Straighten the camera a bit. 30 dB of attenuation. 18 megs, 31 dB. 21 megs, 31. I'll go to 25 megs for the 12 meter amateur band. 31. Then we'll go to 29 megs, that's 31. No, 30, that's 30 there. I've used, 8 turns in total. That's what I've read about this. So that seems to be about the best. You can add, it depends where you want to go on the HF band. For example, if you're an LF type band, top band 80 meters around there, I think you can alter the amount of turns. I've used RG8, by the way, the so-called Mini X, you know, the Mini X stuff. It does say to use that. I've tried to do it as per the book, if you like. Now they reckon up to 40 dB attenuation. I'm not getting that. What was the most? 31 or something. I could probably change the amount of turns to increase it, as I said, on certain parts of the spectrum. I might do that at some stage because I am more interested in top band 80 and 40, and the 5 meg frequencies as well that we got here in the UK. But I'm really pleased with that. They're not cheap. These, what's that, £11 with postage? £11, so it's not cheap. You can put two together, stack them as they put it, stack them up, and then do it. And you really get some attenuation. Then it depends how far you want to go, doesn't it? I mean, where do you stop? Anyway, that's that. I won't be on this video because I'm not going to wait for the postman to turn up again. But the next stage will be to put that into a plastic box with probably a SO239 socket each end. And then I can do some various tests with it actually on the aerial, on the line, and see what happens. So I hope you found some of that useful. Just going to mention something else you can do with the NanoVNA. Watch this. You can check crystals. The crystal freak. I've got a bag of crystals here. Look. Now there's one. There it is. This one, it says on it 5000.00K. So that should be 5 megs. I put it on here and it reads, what was it, 4.9988 megs. So how about that? Nothing difficult about it. You just clip the crystal onto your leads. I was going to show you how to use this NanoVNA, but I'm going to save that for the next time. They are that in both ports, and up comes the crystal frequency. You've got to find that that was the fundamental. Some of these crystals, bear in mind, are used on harmonic or overtone. I'll make a separate video about how to set up and use the VNA when you're doing this, and finding crystal frequencies. Quite interesting finding these, because it will show, there goes the repeater, that's our local 2 meter repeater. There we are, GB3RW. So if ever you're in the area, look out for that one, 2 meters. As I said, I'll show you on another video about the crystals. It shows for someone's bound to ask, yes, it will show the series resonant frequency on the screen and the parallel resonant frequency. So yeah, really useful. Yeah, you've got a bag of crystals. I mean, some of these are unmarked, and the only way to do it in the old days to find out what frequency the thing was on, actually was fundamental frequency, was to stick it in a little crystal oscillator. I made one in a tobacco tin in the 60s, little transistor oscillator, PP3, crystal sockets on the top, different sizes, stick them in there, then tune around on the radio, on a communications receiver, yeah, see where they are. The reason they use overtone, if I remember, years since I've looked into crystals, crystals above, when you get to VHF, the crystal material itself, the quartz, is very, very thin. So they use a lower fundamental frequency, then use the overtone of it. I remember the old days when they were in what the holder's called, the old Bakelite holder. You could take the cover off, take the crystal out, like between 2 bits of metal, take it out, then get some Ajax or Vim, as we had, rub it down with a cloth, grind it down and change its frequency. I've done that a few times. Sorry about my shirt changing every 5 minutes. I've done this video in various bits over various days. Another thing with crystals, very briefly, deviation, FM deviation. Take for example the band 2 VHF FM broadcast band. I think the dev there is what, 75 kilohertz. That is a lot. So you do it low level. If you do it way down low on a low crystal frequency, that you've only got to deviate it a little bit, because when you multiply it, double, treble, whatever, the frequency, you're also multiplying the deviation. That's how they get the wide deviation. Anyway, we're not here to talk about crystals, are we? Okay, I hope I haven't bored you too much. I hope you haven't gone up the pub. Are they open yet? No, they're not open yet, are they? Anyway, I hope I haven't driven you to drink. The next video I'm going to do will be about the NanoVNA and how to set it up and how to do this. I only showed you the results, and also how to check crystals. So that will be the next video. Right, that's it. I've waffled enough. Take care. See you soon. Bye bye for now.